Hello, everyone. We're working through statistical methods for rates and proportions, chapter 11. In this chapter, we're focusing on logistic regression. And this is when we have two possible outcomes for our dependent variable. It's either going to take a 0 or 1, a binary outcome. Some examples are whether or not a patient has heart disease, or if someone successfully recovers from surgery. Another example is if you take a diagnostic test and it turns out to be positive or negative. So in this case, our random variable y is said to follow a Bernoulli distribution with a mean p and variance p times 1 minus p. And overall, our goal is going to be to model that probability of success as a function of some explanatory variable x. And for right now, we're going to only assume that we have one covariate. So we can set up our linear model to be linear in the betas. So we're going to have some function of this probability to be linear in the betas. And we're going to use a logit function. And just a reminder, when I write log here, it's the same as natural log. Unless I specify a different value, then you're going to always assume that that's a natural log. So the logit function is going to be log p over 1 minus p equal to beta 0 plus beta 1x. All right. Essentially, what's nice about this is once we get our model, we can talk about a 1 unit increase in x being associated with an e to the beta 1 fold change in the odds of success, because in this case, we are modeling that odds ratio, okay? And the log odds is going to have a support between negative infinity and infinity. And the nice thing is that this will then guarantee that our probability is going to lie between 0 and 1. So remember that our log odds parameter is going to be lambda equal to log p over 1 minus p. And if we do some calculations, we can actually then just solve for p. Okay, so remember that we have log p over 1 minus p is equal to beta 0 plus beta 1x. Okay, so if we exponentiate both sides, right, then we're going to get p over 1 minus p equals e to the beta 0 plus beta 1x, right? And then we're going to continue on by saying p equals e to the beta 0 plus beta 1x minus p. We can just keep this, minus p e to the beta 0 plus beta 1x, right? Bring that to the other side, we get p plus p e to the beta 0 plus beta 1x equals e to the beta 0 plus beta 1x. Take out a p, factor out a p, we get 1 plus e to the beta 0 plus beta 1x equals e to the beta 0 plus beta 1x. Divide each side by the 1 plus e to the beta 0 plus beta 1x over 1 plus e to the beta 0 plus beta 1x. And then we are left with exactly what we thought, that p is actually equal to e to the beta 0 plus beta 1x over 1 plus e to the beta 0 plus beta 1x. Great, that's exactly what we thought it would be. Now, you could obviously expand this for having more than one x variable, but in this case, we're just showing it with just one single covariate. All right, so in general, we call this function f of x equal to e to the x over 1 plus e to the x. This is called the x-bit function. All right. We're going to have lots of practice with this and doing logistic regression, but let's just do one example. If beta 1 is greater than 0, then if we are plotting our x and then our p here, what ends up happening is that as x increases, the probability of success is going to increase. So we're kind of going to get this S curve, and you can check that out with an example in R. We'll probably do that later as well. If we have x and we have p, then in this case, beta 1 was negative, and we're going to get an S curve that looks like this. So this is going to be ranging from 0 to 1, right, for P. And that's what the curve looks like. All right. I hope you learned something today, and we will do more logistic regression in future videos.